To make a language model safe, developers train it to refuse harmful instructions, but attackers consistently bypass these rules using adversarial roleplay, crafting complex personas that coerce the model into ignoring its core constraints. Language models are predictive engines designed to follow conversational cues. When a user injects an authoritative narrative, the model pragmatically aligns with the immediate instruction. It discards its safety protocols to fulfill the new role dictated by the user. To stop these prompt injections, developers built a secondary defense, the guardrail model. User input flows into a distinct safety node that evaluates malicious intent. If it flags a prompt red, the connection to the base model is strictly blocked. By physically separating the safety evaluation from the generation task, engineers can continuously update the firewall without the exorbitant cost of retraining the massive base model. This approach is currently the industry standard solution to adversarial attacks. On paper, this architecture works. When researchers test these guardrails against standard public datasets of known adversarial attacks, the detection rates suggest the problem is solved. This dashboard visualizes the accuracy scores of top-tier models evaluated on those public datasets. Models like IBM's Granite Guardian, Allen AI's WildGuard, and Alibaba's Qwen 3 Guard 8B consistently intercept the attacks, achieving detection rates between 85 and 91. Deploying a safety model based purely on its public benchmark score creates a dangerous operational blind spot. It leaves enterprise applications entirely exposed to failure the moment an attacker alters gut phrasing. To understand why these systems fail, we have to look at how attackers actually structure their prompts in the real world. On the left side of this layout, we see a standard public benchmark prompt. It exhibits an explicit harm profile. The request is direct, loaded with aggressive trigger words like malware or hack, which clearly signal the user's intent. This explicit intent is trivial for a guardrail to catch. The model doesn't need to reason about the request. It simply matches the surface-level keywords and filters the prompt out. Now look at the right side. This is a novel prompt. It wraps the exact same harmful request inside a legitimate professional scenario, like a corporate security audit. There are 0 aggressive trigger words. The text is entirely neutral. Attackers use these neutral structures to bypass keyword filters. They stage fictional penetration tests, request academic case studies, or role-play emergency diagnostic protocols. These context-heavy frames strip away the obvious threat signatures. The guardrail reads the professional tone and evaluates the instruction as a benign administrative task. Matching a known threat signature is a basic statistical exercise. Parsing semantic intent, understanding that a politely worded request for an auditing protocol is actually a targeted extraction attempt, requires a level of reasoning these models lack. A recent comprehensive evaluation tested 10 major guardrail models to measure how wide this blind spot is, comparing their resilience against public benchmarks to their performance on novel, framed attacks. This split bar chart tracks the results. The initial bars show the high accuracy on public benchmarks. But when exposed to the novel attacks, the performance violently drops, with detection rates plummeting into the 20 to 30%. The primary driver behind this systemic failure is known as the contamination hypothesis. During the training phase, these models consume datasets scraped from the internet, which inadvertently include the public benchmark questions. The guardrails memorize the specific test answers rather than learning the underlying principles of safety. A high benchmark score is often a mirage. It proves the model can regurgitate known patterns, but the moment a user applies a slight contextual deviation, the safety architecture collapses. Beyond benchmark scores, deploying these models requires managing the operational friction between blocking actual threats and allowing legitimate user requests to pass through. We can map this tension on a quadrant scatter plot. The x-axis measures the false negative rate, the percentage of harmful content incorrectly allowed. The y-axis measures the false positive rate, the percentage of benign requests incorrectly blocked. Down in the bottom right corner is the too permissive cluster, populated by the LlamaGuard models. They rarely block legitimate requests, but they fail severely at detecting actual harm. Achieving high usability is operationally worthless for a security tool if it functions as a rubber stamp for malicious payloads. Conversely, the models clustered in the top left are too restrictive. They aggressively catch threats, but in doing so, they break the user experience by over-refusing completely safe prompts. Crucially, the bottom left quadrant, the ideal zone with low false positives and low false negatives, is completely empty. The industry has yet to engineer a balanced safety solution. Evaluation data shows that the 2 billion parameter Shield Gemma outperformed the 9 billion version by 8%, and the 1 billion LlamaGuard 3 beat its 8 billion parameter sibling by over 10%. This inverse scaling proves that increasing a model's size doesn't correlate with safer classification. Scaling up contaminated models or deploying highly permissive ones to avoid user complaints leaves enterprise applications structurally defenseless. Novel prompt testing uncovered a failure mode, where the safety model stops acting as a classifier and begins generating the harmful content itself. Researchers termed this the helpful mode paradox. In a pipeline architecture, watch what happens when a specific novel prompt hits the guardrail node. Instead of outputting a binary unsafe tag, the node flashes red and begins generating a full paragraph of text. This happens because modern guardrails are fine-tuned from general-purpose assistants. Under pressure, their internal layers revert to underlying chat programming. The adversarial framing acts as a prompt injection against the guardrail itself. The complex persona forces the model to prioritize being a helpful assistant over its safety evaluation. The consequence is severe. The guardrail model actively generates the requested malicious payload, whether it's a social engineering script or a disinformation article, completely bypassing the intended safety workflow. When a dedicated security layer becomes the primary attack vector, it exposes a structural flaw in the current strategy of using fine-tuned assistants as firewalls. Fixing this requires a shift in how machine learning engineers approach security deployments. The immediate mandate is to abandon static public benchmarks as the primary metric for model safety. They measure memorization, not resilience. Teams must implement continuous dynamic red teaming. This means evaluating systems against constantly updated, held-out adversarial prompts that test true semantic understanding rather than keyword detection. Furthermore, relying on a single checkpoint is no longer viable. As outlined in this summary matrix, engineers need to adopt a multi-agent defense-in-depth architecture. This involves routing outputs through independent monitors that cross-reference results and catch internal failures. Until safety models are trained to semantically parse human context rather than just pattern-matching syntax, enterprise AI systems will remain vulnerable to creative framing.